Hello everybody. We're doing section 2.6 on continuity. So I think the best way to start, instead of saying what continuity is, give you examples of discontinuities. So once upon a time, you may have heard this when you were younger. How do you know if a function's continuous? And you may have heard a teacher say, a function is continuous if you can draw it without lifting up your pencil. So let's take a look. So if I'm tracing this and drawing this, I have to stop right there, lift up my pencil, and then continue on the other side. Let me do that a little thicker so you can see what I'm doing here. So once again, if I'm doing this, I'm drawing, I have to stop there, pick up my pencil, and continue on the other side. And you probably intuitively can see that we have a discontinuity. We have an issue here. So there's a hole here, there's a gap. So since there's a gap, there's a discontinuity. This is known as a removable discontinuity. In the past, you may have heard that referred to as a hole. So that's something that's been called, it's been called in the past a hole, but this time it's a removable. I have a guess why it's called removable, but we'll talk about that. Now if you look here, if we draw this one in the middle, I have to stop, lift up the pencil, come up to the top, and finish this graph. So again, that idea of being able to draw without lifting up your pencil shows continuity. And then the last one, we have the issue. As I'm drawing, clearly I have to stop. And then on this side, the infinite asymptote, it goes up forever. And even if it was an asymptote on both sides, I'd have to pick up the pencil and move to the other side, or pen. So we see the issue with when things aren't continuous, it kind of looks obvious. There's jumps, holes, there's gaps, there's issues. So what is the official definition of continuity? We will take a look. The definition of continuity. All right, so let's take a look-see here. I will highlight some stuff with red. So how do you know if a function is continuous at a specific point A? Well, this if and only if, it means if the first statement is true, then the second must be true. And also if the second statement is true, the first must be true. So what do we have going on here? We have the limit as x approaches a from the left must be the same as a limit as x approaches a from the right must be equal to the function at the point. So that is the formal definition. The book also mentions, I can't remember, it's not the definition, but they give you the checklist, continuity checklist. I would ignore that. When you're doing a proof of continuity, you would want to be showing these three statements, and they all equal the same thing. And we're going to look back at the examples above and see why this makes sense. So in the first one, if I find, I got to make some values up. Let's suppose that is L. And let's suppose this value there is M. That will help us kind of see what's going on here. So let's do the continuity test on this first one. So I would take the limit as x approaches a from the left of my function f of x. And if you look at that, what we have here, I'm approaching a from the left. The y value approaches L, so that's going to be L. Then I need to take the limit as x approaches a from the right, so that's my next step. So I want x approaching a from the right of my function. And if we approach a from the right, coming this way, the y value also approaches L. So everything is fine and dandy. But then here's a question. What's the value of the function at a? And if you look at a, where is the dot? It's right here. That's at m. So where does it fail? It fails, and let me label these. Statement 1, statement 2, and statement 3. 1 and 2 are equal. They both are L. But statement 3 is M, so they don't all three equal. So therefore, it fails a continuity test because it doesn't equal f of a. Now I want to make one comment here before we move on. Notice number 1 and number 2 can be summarized as one statement. That could be summarized as a limit as x approaches a of f of x equals f of a. So this is an equivalent statement, but in general, when we are trying to prove something, we'd have to show the left, then the right, then the value at the point. Like I did here, the left, then the right, then the value at the point, to show continuity at a specific point. All right, that's it for that one. That's what they said here. The limit as x approaches a does not equal f of a. Well, these are both L, so this limit's L, and that's m. Well, what's going on here? I need to take the limit as x approaches a from the left, and I need to come up with some values again. I'll call that L, and call this value here, I'll call that m. So that is going to be equal to L. No, I'm a liar. That's going to be m, isn't it? So I'm approaching a here from the left. The y value gets close to m, so we'll call that m. Then I take the limit as x approaches a from the right of f of x. As I approach a from the right, that's L. Clearly, these aren't equal to each other. So it fails. 1 does not equal 2. Therefore, it is not continuous, and that's a jump. And that should make sense. From the left and right, you go to different values. Clearly, that's a jump between them. And then the last one, the infinite discontinuity. If we find, I need to give values again. We'll call this point L. So we take the limit as x approaches a from the left. That would get us L. The limit as x approaches a from the right, that would be infinity. And then if you wanted f of a, that would be does not exist. Nope, liar, liar. That's L also. I thought there was a hole there, but that is not a hole. That is L. So anytime you have an infinity anywhere, these could both be positive infinity, by the way, and you would still have a discontinuity, an infinite discontinuity. Whenever one of these limits is infinity, you have an infinite discontinuity, because even if they both went up to infinity, they're not connected. There's a discontinuity there. And this one, if you wanted to find f of a, you would have been m for the middle one. But we were done already because this did not equal this, so this was not true. So we were pretty much done at that point. So I will give you one more example on this redo of the video. I'm going to come up with a piecewise function. And I'll have two pieces. We'll have x squared plus 1 for x greater than or equal to 1. And then I will have 2x minus 1 for x less than 1. And we want to check for continuity. Is f of x continuous at x equal 1? So first, we have the limit as x approaches 1 from the left. Now, the question is, which function would I use for this case? Well, the left of 1 is smaller than 1, so this is x less than 1. It's going to be 2x minus 1. And that is a polynomial, so the shortcut, we plug 1 in there, and we get 1. Now we find the limit as x approaches 1 from the right of f of x. Now, which function would we have to use if we're approaching from the right? That's bigger than 1. It's going to be x squared plus 1. And that's going to get me 2. We already know it's not continuous. And the reason? Because the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right. That's our justification. We're done. And as a side note, if you wanted f at 1, in this case, I would use this top function because that's where it equals. That would end up with 1 squared plus 1 or 2. You don't need that because we already have a discontinuity based on this. So that's an example of using the definition of continuity to show that something is or isn't. All right, this section, pretty fast, pretty easy. If f and g are both continuous at a, then if you add the functions together, it's still continuous. If you subtract, they're still continuous. If you multiply them, they're still continuous. If you take a continuous function and raise to the power n, where n is an integer and it's positive, then that's still continuous. If you divide 2, and I probably should add this, I don't know why I don't have it, that's also continuous as long as g of a does not equal 0. So I want to add that to that. That's important. And the last one is saying this. C is just some number, a constant. So if I multiply a continuous function by a constant, the new function is also continuous. So I'll just give you a quick example for this. This one's pretty straightforward. Let's see, the square root of x is continuous. I'll call that f. We'll let g be, I don't know, let me think, sine x. Technically, you don't know this is continuous everywhere right now. Intuitively, you know the sine x function. If you graphed it, it looks continuous everywhere. So I'm going to assume those are continuous. Then, f times g, which is square root of x times sine x, that new function is also continuous. Or f plus g, which is square root of x plus sine x, that function is also continuous. Or 3 times f, which is 3 radical x, that also be continuous because that's just a constant times the function. So that's a quick example. That's a pretty easy one. You'll like this one. We already kind of did this one before. But all polynomial functions are continuous for all x. So you know a polynomial function is continuous everywhere because polynomial functions, they just look like whoops. So those are all continuous. That's important for you to know. And then a rational function is continuous. A rational function is a polynomial divided by a polynomial. So a polynomial divided by a polynomial is continuous. So we already knew that one because we have this statement. If you divide two continuous functions, then it's continuous as long as the bottom's not 0. So the same thing here. We learned that polynomial functions are continuous. So if you divide 2, they'll also be continuous as long as the denominator is not 0. So that is a pretty straightforward theorem. And a theorem is something that's been proven, so now we can use it. So any theorem given in the book, we can assume to be true, and we can use that. And so that's polynomial and rational functions. Composite functions. So you have two continuous functions. G is continuous and f is continuous at g of a. Then if you plug one into the other, it's still going to be continuous. I'll give you an example of this one. Let's say f is square root of x, and g is, I don't know, I will do sine of x. All right, so what if we do f of g of x? What is that? That's taking the g function and plugging it into the f function. So that's going to be square root of sine of x. Is that continuous? Well, it's continuous as long as f is continuous at all values of sine of x. Well, here's the thing. Sine of x can be negative, right? And f doesn't exist where sine's negative. So this would be continuous as long as sine of x is positive or 0. So that's what's going on here. You plug a function into a function. If both are continuous, then the new function will also be continuous. Pretty straightforward. Now, before I do this one, I want to note something to you that's very important. So we had the definition of continuity earlier. The limit as x approaches a of f of x equals f of a. So we would say f of x is continuous at x equal a if and only if. And again, a reminder, if and only if says if the first statement's true, then the second one's true, and if the second one's true, then the first one's true. Now, this has implications that are greater than you realize. So here's what it's saying. If you have a continuous function, okay, and you're trying to find this limit, you don't know that limit, what you're able to do now is plug the point into your function, and that gives you the limit. I'll say that one more time. So when we're trying to find limits in the previous section, we had to plug in points or do different techniques to find that. But what I want to say to you, now you have a new thing. If a function is continuous, to find the limit, all you have to do is find the value of the function at that point. You no longer have to do any other fancy schmancy techniques. All right? We kind of been using that, but now we know why that works. It's got to be continuous. Then the limit is the function at that point. Now we are able to do that. That is a big step forward for us. Make sure you understand that concept that I just threw out at you. Okay? Now, Theorem 12 or 2.12 is basically the same thing as Theorem 2.11, but slightly different, because this one's talking about limits now. The previous one was talking about continuity. Now this is talking about limits. So, and it kind of is related to what I said. If you want to find the limit, you just plug the value of the point. You get the value of the function at that point. Well, kind of that's what's happening slightly. So here's what's going on. You're trying to find this limit. Well, the shortcut that we kind of talked about is you can just find the value of the function at this point. Well, that's what's happening now. I can find the limit of the inside part, then just plug it into my function f directly. But how do you find the limit of this? Well, if g is continuous, Then I plug a into my g function. Then I plug that answer into the f function. Hopefully that makes sense to you. And the second one is saying the exact same thing, just worded differently. So let me do an example for you. All right, example. Let's do f of x equals sine x. G of x equals, let me do a nice function. I can't think. Oh, square root of x. Okay, yeah, no, I don't want to do that. Oh man, I want easy numbers. I shouldn't have. Here, let me switch this up. Sorry guys. I don't want to make this hard. Let's make this the square root of x and make this the sine of x. Maybe I can handle that. Okay, then f of g of x, what would that be? Well, that I plug g into f, that would be square root of sine of x. Now suppose I want this, the limit as x approaches pi over 2 of f of g of x. So that's what's happening. We want the limit of this. G is continuous for all a and f is continuous. Those are true. So I can do this. This says this is f, the limit as x approaches pi over 2 of the sine of x. So I'm taking the limit of the inside function, which is g of x. Well, that's going to be 1. Because the sine of pi over 2 is 1. How do I know that? Sine's continuous. You're going to know that in a second. And to find the limit, all I do is plug pi over 2 in because it's continuous. And sine of pi over 2 is 1. Then I can plug that into the f function. But the f function is square root, so it's going to be square root of 1, which is 1. All right, so that one is kind of looks weird, but it's actually more straightforward than it looks. All right, Theorem 2.13, continuity of functions with roots. Okay, m and n are positive integers, important. No common factors. That just means this fraction is fully reduced. Nothing will cancel out. Okay, so it says if m is an odd integer, then f of x raised to the n over m power is continuous for all points at which f is continuous. Wow! These things seem so weird, but let me explain. Let me give you an example of what this is saying and why this makes sense. So let's do a function. I like sine. And we're going to raise it to a fraction. Let's say 3/5. I like that number. Well, let's see if it meets the qualifications here. So m and n are both positive. Yes. No common factors. I cannot reduce this. Yes. M is odd. 5 is odd. Then this whole thing is continuous for all points where f is continuous. Sine is continuous everywhere, so this should be continuous everywhere. And why is that true? Here's what you have to understand. That top number is the power. Ooh, that's bad. Can't see that. The top number here is the power, and the bottom number here is the root. You have to know that. If you don't, you need to just get to the point where you just know that. Very important. So I can rewrite this as the 5th root of the sine of x raised to the 3rd power. Now, here's why odd is important. Can I take the cube root No. Can I take the square root of negative 1? No. Does not exist because that's an imaginary number and we're dealing with real numbers. Can I take the cube root of negative 1? Yes, that's negative 1 because negative 1 times itself 3 times is negative 1. So a negative number 3 times will get you negative. Here, a negative 1 squared can never be negative, so that's why you have problems. Same thing with the fourth root. That does not exist because anything times itself 4 times will always be positive. How about the fifth root? Yeah, that's negative 1 because negative 1 times itself 5 times is negative. So here's the thing. If I have an odd power root, I can take the root of anything. So that's why this works. This is an odd power. Excuse me. Bad. I just lied to you again. Fifth, it's an odd root. If you have odd roots, you're able to take the square root of a negative number. Therefore, this is good always. Now, what is the second one saying to you? What if m is even? If m is even, not even. So let's come up with an even one. I'll do 3/4. You have to realize this is the fourth root of sine of x cubed. You can't take the fourth root of negative numbers. So what must be true? That's why they make this statement here. It's continuous for all points at which the function on the inside, when the function inside is positive. This is only true when sine of x is positive. That's all they're saying in this. So basically, if you're taking a root of a function, if the inside function is continuous, then the root will also be continuous as long as the inside's positive when you have an even root. That's all that's saying 213. Let's move on. If a continuous function f has an inverse, so if a function has an inverse, then the inverse is also continuous. I'll give you a quick example of that, of what that means. So say f of x equals x cubed. The inverse of that will be the cube root of x. Well, there's a rough graph of x cubed. What's the inverse of that look like? It's going to look like that. And that's cube root of x. So if the original is continuous, no jumps, no gaps, then the inverse will have no jumps and no gaps because the inverse is just reflected over the line y equals x. The x's and y's just get switched. So that's what that is saying. This is a nice one. I don't have to say a whole lot. Now you know all trig functions are continuous, all inverse trig functions are continuous, and exponential functions are continuous, and log functions are continuous with one caveat on their domain. So sine and cosine have a domain of positive to negative infinity. They exist everywhere. But you have to realize something like the tangent has a domain. What does a tangent look like? It's a bunch of these, right? And you realize there are asymptotes. So we have continuity all in this part of the graph, but at the asymptotes, the function doesn't exist, and those are the points where we don't have continuity. So all of these will be continuous everywhere except where it doesn't exist, and all four of these are going to have asymptotes. So these are continuous as long as there's not an asymptote at the point you're looking at. Let's move on. And the log, you guys all should know what the log function looks like. That's the log function. So you should know it's continuous everywhere where it exists. It only exists where x is greater than 0. It does not exist to the left. Therefore, it's only continuous from x is greater than 0. All right. We're getting through this. We're down to the last one. Intermediate value theorem. This one looks crazy. Reading this, you're like, what? So as I go through an example, hopefully it makes sense. Now, please watch this until it makes sense. This theorem is used all the time. I guarantee you it's going to appear on your FRQ test this coming May when you take the AP test. This will be used, and you look at it, your brain's going to hurt. You look at it again, your brain's going to hurt again, but eventually it's going to make sense. So let me go through. F must be continuous. That's why it's in the section of continuity. And it must be continuous on A to B. That does not mean a point A to B. You have to understand what that means. So I will explain to you now. This is x, an interval from x equal A to B. So we're looking at this first example here. Here's A and here's B. Is this function continuous? Yes, no jumps, no holes, no gaps. Where is it continuous? From A to B, including A and B. So another way to write this is this. That's another way, it's a shorthand way, set notation, all points between A and B, including A and B. When you have brackets, that includes the endpoints. When you have parentheses, you shouldn't have equals because it doesn't include your endpoints, okay? L is a number strictly between f of A and f of B. Well, here's f of A, here's f of B. L can be any number that's strictly between it. What does strictly between mean? I will interpret this above. That means L must be between f of A and f of B, or I could do this too. Now, you could either write those conditions or say L is strictly between f of A and f of B. Strictly between means it can't equal the endpoints. That's why I don't have equals here. It's between. F of B could be bigger than f of A, so I need this, but f of A could be bigger than f of B, so I need both these statements. This is another way of saying this. All it's saying is L is a number that's between f of B and f of A, and it can't equal f of B or f of A. Cannot equal, it's between. So those are the conditions that must be true. So first, continuous from A to B, and you need a number L between f of A and f of B. Then what's your conclusion? There exists at least one number C. There's my C. C must be between A and B. So this statement here, I can write it like this. Whoops, the C instead of that, sorry. There at least one number C. This statement, C in the interval from A to B, means C is between A and B. So your C is between A and B, but not including A and B. It cannot be A or B. It's in between those. So there's going to be some point C in between A and B such that f of C equals L. Well, f of C is right there. This is f of C. So just to summarize in layman's terms, if L is between the endpoints of your function and your function's continuous, your function must cross L. It must equal L at some point C. That's all this is saying. This, please take the time to make sense of it. I know you might look at it and your brain might hurt a lot, but get to the point where it makes sense. Now we're going to look at the second example here, and then we're going to scratch our heads. So we have f of A and f of B, and L's between them, right? So that fits. L is between f of A and f of B. But there is no point in this area. There's no point where the function equals L. It doesn't cross L. So somebody say, hey, I thought the intermediate value theorem says this function has to cross this L point. Why doesn't it? Because it doesn't follow this. F is not continuous. There's a jump discontinuity. Therefore, the intermediate value theorem doesn't have to apply. That's why there doesn't have to be an L or a C where that's true. Now, there could have been, even though it doesn't meet these conditions, it might cross L because this function could have looked like this. So it could cross L even though it doesn't meet the condition, but the mean or intermediate value theorem will not apply unless it's continuous on a closed interval and L is between the endpoints. So that's why this doesn't apply. Now, why does it say at least one? At least one. Well, here's an example where the function crosses 3 times. There's actually 3 points where the function equals L. So this is saying there's going to be at least one. There might be more, but you're guaranteed it's going to cross once. So that's the example of the mean value theorem. Well, that's an explanation. I'm going to do an example. I'm redoing this video, so if you're watching this video for a second time, it's changed. I can't remember the, well, let's see if I remember. I will make up a function, f of x equals, did I do sine x? I'm trying to remember what I did. And we're going to put it on the interval. On the interval from 0 to pi over 2, show, oh no, it was pi over 3. I remember now, yes. 0 to pi over 3. Show that f of x equals radical 2 over 2 on the interval between 0 and pi over 3. So you have a continuous function. We learned sine is continuous. You have a closed interval, and you want to prove that your function is going to equal some number. How do we know it's going to equal radical 2 over 2? Here we go. First statement I'm going to say, sine x is continuous on the interval from 0 to pi over 3. How do I know that? This is the answer. Because I just had the theorem earlier that the sine function's continuous everywhere. So we have the statement the sine function is continuous. Now, that meets this first statement. I need to show L is between f of a and f of b. Is it? F of a, in this case, would be sine of 0, which is 0. And f of b, in this case, would be f of pi over 3, which is sine of pi over 3, which is radical 3 over 2. Okay, so I found f of a and f of b. Now, is the value I'm trying to show, is that between 0 and radical 3 over 2? I say yes. So here's my next statement. F of 0 equals 0, which is less than radical 2 over 2, which is less than radical 3 over 2, which is f at pi over 3. So what have I done? have just shown that this point here is between the endpoints. It's between the endpoints. So we have met the conditions of the mean value theorem, or excuse me, intermediate value theorem. We showed the function's continuous on a closed interval. We showed L, the number we're looking for, is between the endpoints. What's our conclusion? I can therefore now say it's guaranteed that there will be at least one C in this interval such that the function will equal that value. So now I can conclude, therefore, those three dots means therefore there exists at least one C between 0 and pi over 3 such that f of c will equal radical 2 over 2. Done. Now you could say, therefore, by the mean value theorem, or intermediate value theorem, sorry. Therefore, by the intermediate value theorem, you could add that, but it's not necessary. You don't have to memorize the name. All you have to do is give the conditions. This must be true, and this must be true. Therefore, the final statement's true. So that's what I did. It's continuous, and we have a point between the endpoints. Therefore, it must be true that there's at least one C between the endpoints such that the function equals that value. That's the example of the intermediate value theorem. That's it for this video. Bye bye.